Hello everyone, myself Devashish Das, Assistant Professor of Electronics Communication Engineering Department of Greater Kolkata College of Engineering and Management. Digital Signal Processing. In this video, we are going to study about the different topics of digital signal processing and its application, how digital signal processing can be applied in different field and how the different topics is present in the digital signal processing. We are going to study about this in these videos. Digital signal processing. This course is mainly for BTech students of Electronics and Communication Engineering of 5th semester. The subject code of it is ECE 504. In this session, we are going to discuss about the analog to digital conversion and the reverse of it. That means from digital to analog conversions. We all know that our whole world is analog and our systems are digital. So to process this thing from analog to digital conversion and converting the digital system to analog, the several steps required. In this session, we are going to cover the following topics: the analog to digital conversions, the sampling theorem, the aliasing, anti-aliasing filter, quantization, encoding, and digital to analog conversion technique. So before we are going to start about our today's sessions, first we have to understand that the whole world is analog. That means here we take an example of telephonic conversations. That means a person speak in a telephone and the voice of that person's is being transferred with the help of telephone network and received by the another user of the telephone, and he or she can hear the voice, and the same way she or he replied to the sender person. To understand this thing, we have to understand the voice is the key criteria or key message in this system. So the voice we are talking is continuous in nature. That means if we convert the voice with the help of microphone and we get a continuous changing in amplitude electrical signal. That means if we speak in front of a microphone and if we analyze the electrical signal of the microphone, we'll get something like this, a continuous varying analog signal. That means the signal is continuously changing with respect to time. The voltage of the signal is continuously changing with respect to time. It is the output of a microphone, and we have to process this continuous signal into digital to transmit with the help of IP network or the internet protocol network, and we have to send this signal to the receiver end. So this is a pretty example of a digital telephone systems, and the reverse process is also taking place. That means our digital signal is being converted into a analog signal to hear the voice of the sender properly. So a conversations always there to convert the analog signal to digital signal and the digital signal to analog signal, and in the meantime in the channel there is some processing of this digital signal. Now we see first, these are the two terminologies in the analog and digital domain. The analog is continuous in nature and it has infinite possible values in 2 points or 2 steps in between points. So analog is basically a continuous in nature in both time and amplitude. In case of digital, it is discretized or discretely value signal such as integers encoded in binaries, and there are several analog to digital converter are also present in this to convert the analog signal to digital signal. So first, the sampling is the fundamental state. That means we require sampling from the analog signal to make it digital. So samples are used in real world, such as our voice call in analog signal, which is to process these signals into computer we need to convert this signal to a digital. Analog signal is continuous in both time and amplitude. A digital signal is discrete in both time and amplitude. To convert a signal from continuous time to discrete time, a process is called sampling, which is used. The value of this signal is measured at certain interval of time. Each measurement is referred to as samples. We'll discuss about these samples. Here it is a signal. We can see a signal, a continuous signal. The green line, it is a green line. You can see a green line that is change continuously with respect to time. The amplitude of the signal is changing continuously with respect to time. So this is a continuous time signal, and we take some samples in certain interval, certain and equal interval, that is t. We can see a interval of t between two samples, and this interval is same for each and every side by side samples. So we take samples from this continuous signal like this. So t is the interval between the two samples. T is the time interval between the two samples. Capital T is the time interval between the two samples, and T is the time axis of these signals. We will take also another examples of it. Sampling can be done for functional varying space, time, or any other dimensions, and similar results are obtained in two or more dimensions. The sampling frequency or sampling rate, Fs, is the average number of samples obtained in 1 second. Thus Fs is 1 by t. So t is the time interval we have seen in this previous pictures, that is t is the time interval of the two samples, between the two samples, simultaneous samples, and Fs is the 1 by reciprocal of this time, capital T. So F is denoting the sampling rate or sampling frequency. A sample is a value or set of values at a point in time or space. A sampler is a symbol or a operation that extracts samples from a continuous signal. A theoretical ideal sampler produce samples equivalent to instantaneous value of continuous signals at desired points. So we'll see how the sampling is done. In this slide we show how the sampling is being done. First, obtain a signal value from the continuous signals at regular time interval Ts, which is a sampling rate, and its reciprocals, that means 1 by Ts gives us Fs, sampling frequency. The result of this process is just as sequence of numbers. Our discrete time signal will be denoted as xn, where n is the index, and as sampling interval Ts is defined, sampling just extract the signal's value at all integer multiple of Ts such that xn equal to n into Ts. At this point, our signal is not a continuously digital because the value xn is still take any number from a continuous range. So we use the term discrete time signal. So we can see the above statements are nothing but just say about this. It is a continuous time signals which is varying continuously with respect to time, and we take some samples from it in equal interval, that is Ts. Ts is the equal interval of two samples, and the inverse of this Ts is the sampling frequency, which is denoted as Fs, and we can take a sampled signal from a continuous time signal. It is a sampled signal, or we can say this is a discrete time signal, but we have to keep in mind this is not a digital signal, it is a continuous discrete time signal, because the amplitude of each sample is not discrete, it is a sampled value of this continuous time signal. So it is a discrete time signal, and in this way we take sample from a continuous time signal and produce a discrete time signal. So here we can see a mathematical representations of the sampling, how the sampling is being done. It is a cost function, and we can represent a mathematical denotions of the sampling, where omega is the angular frequency. So in this way we can get a mathematical representation of a sampling. Now we will discuss the sampling rate and its comparison. That means how the sampling rate provide impact on the sampling process. We will discuss about it, and we take in this example two sampling rate. One is 2240 and one is 1240, and another is 1000 samples per second. First one is 240 samples per second, and in second case it is 1000 samples per second. So we can get the sampling time, that is Ts. For the first case it is 4.166 milliseconds, and for the second case it is 1 millisecond. Here we can write a MATLAB code to plot this sampling rate for the cos signal. Here we can see a cos signal cosine function, or we can say it is a cosine function. It is continuous in time. We plot this signal and we take samples. For first case it is 240 samples per second, and for second case we take 1000 samples per second, and we will make a comparison in the coming slide with respect to this sampling rate. Now we will discuss about this continuous time, and we will get Here we can see a continuous cosine functions as we have discussed in the previous slide. It is a continuous cosine functions, and in for first case we take 240 samples per second and we can get this type of graph. It is a discrete signal. These are all discrete time signal. And for the second case, for 1000 samples per second, we can get a graph like this. It also a continuous discrete time signal. So the rate of sampling makes a very well effect in case of discrete time signal, as we can see from this graph. You can see that if the sampling rate are more, we can get a good resolution of the signal. That means the signals look like more resolute or more analogous or more similar to the continuous time signal. And if we take a less sample per second, we can get a not so much good or not well resolution of the signal. That means the resolution of signal get hampered due to less sample. So this is the important conclusion of this topic, that if we take more samples, the resolution of the signal will be more, and if we take less samples, the resolution of the signal may get hampered. So sampling theorem states that a continuous time band limited signal may be represented by its sample and can be recovered from its sample, provided that sampling frequency omega s is the sampling frequency must be greater or equal to 2 omega m. That means the maximum frequency of the signal. That means the maximum frequency presence in the signal, in the input signal. The condition is referred as the Nyquist criteria, and this condition is referred to as Nyquist criteria. So it is a very important statement for all of us, that sampling theorem is a very important statement. It states the nature of the discrete time signal. The theorem states us that the sampling frequency should be greater twice the maximum frequency presence in the input signal. Input signal can be consist of many frequencies, so for the sampling frequency, that frequency should be greater than the twice the maximum frequency presence in the input signal. It is the sampling theorem, and this theorem is very important for all the students. Now we take an animations of this sampling and the whole process. Just take an example and have a look.
Before learning about sampling theorem, let us first learn what is meant by sampling. Sampling means taking a sample or samples from a population which gives the entire detail about the whole population. To be more precise, taking a sample of food gives us the taste of whole food. In data communication, sampling means taking sample of signal at equal intervals which gives the entire data about the sampled signal during reconstruction. Now, let's see an application of sampling, encoding, decoding in data transmission. Consider a person sends a voice message to another person. The voice of the person is an analog signal. This analog signal is sampled at regular time interval so that it can be reconstructed to original analog signal. The digital data is encoded for security purpose and to avoid loss of data while transmission. At receiver side, the encoded signal is decoded back to the digital data. From the sampled digital data, the original audio file is reconstructed and the receiver hears the voice message. From this, we learned that sampling is used to convert the analog signal into digital signal, and we also learned that encoding and decoding plays an important role in data communication. Now, let us learn about sampling theorem in detail. Sampling theorem. A band limited signal can be reconstructed exactly if it is sampled at a rate at least twice the maximum frequency component in it. The maximum frequency component of G of t is Fm.
Thank you for watching. If you have any queries, you can contact to me. The contact number is given. The same number can be used as WhatsApp number. If you have any queries or doubt, you can call me or WhatsApp me to this number. Thank you very much.